Now I need to tell you what a polymorphism is. Okay. Hopefully, any questions about CS, please? Okay, maybe I'll just leave it there for 1 second. I mean, this is horrible to read, so don't look at this. So, the subscripts to 4 depth. Okay. So, it's basically problems like 3-SAT, to graph coloring, etc., abstracted in a general way. So, what is a polymorphism? A CSP is specified by a predicate. So, we are going to also define, so we are going to capture its complexity by something called the polymorphism of the predicate. So, what is a polymorphism of a predicate? It is a function from d to the m to d, where m is some arity of the polymorphism, which can be up to you. If whenever the following happens, when is it a polymorphism? If the following holds. If you take an arbitrary set of m tuples which satisfy P of your choice, and then you take them, you apply your f. Now, f can be applied to d, m elements of d. So, you can apply f along the columns. Now, apply f along the columns, you are going to get a new row, a new tuple that should also satisfy. Okay, I will give examples in the next slide. So, it is basically a closure property, higher order closure property. If I take m solutions and I combine them using f, I will get a new solution. Okay, that is exactly what I have said down here. And the set of all such functions is called polymorphisms of P. Now, you might wonder if this is even exists or is, is empty. It always exists because you can have these functions f of z which simply outputs the ith coordinate. What that means is that when I take these m tuples, I simply copy the ith tuple down here, and that is of course going to have this property. So, these are called dictator functions because they ignore everyone else and just go along with one person. Okay. So, these always exist. So, this set is non-empty. Now, the question is whether there are anything interesting besides dictators. Okay. So, that is the point. Okay. So, again this is the definition. Another way to think about it is that if you take an m by k matrix whose rows satisfy P and you apply f column wise, you should get something that satisfies P. Okay. I just wrote down the definition. Now, for 2 coloring, we already saw this, such a polymorphism exists. If I take 3 rows which satisfy, all the 3 rows are 0, 1, 1, 0, 0, 1, they are unequal, then applying majority will give me a pair which is unequal. Okay. So, majority 3 is a polymorphism for this, which is non-trivial, not a dictator. Let us do one more example, and actually thanks to Dima Zouk here for mentioning this as a good way to motivate. So, you might see it in his talk later too. So, Pxy is 1 when x is lesser equal to y. So, it just checks if one element is lesser equal to y in some the integers. And then if you think about it, you are basically saying if I give you pairs which are all lesser equal in each row, I apply f, I should get something which is also lesser equal. And if a moment's reflection will tell you that in this case any monotone function is a polymorphism. That is the definition of a monotone function. Coming back to another example, if P is checks number of 1s among a triple. So, it takes 3 things and it outputs 1 if there is 1 or 3 1s and 0 if there are 0 or 2 1s. Okay. In this case, what is a polymorphism? I can take 5 triples like this. Note that each row has an odd number of 1s and 5 just because it is an odd number, any odd number works. And I can simply take the XOR along each column and that will also have an odd number of 1s. Okay. And therefore, this parity function on 5 inputs is a polymorphism. Why is that? Simply a parity argument, right? Each row has an odd number of 1s and there are an odd number of rows. So, the total number of 1s is odd. So, the number of columns with an odd number of 1s must be odd. Okay. If you understood it, it's fine. If not, you can reconstruct it. So, this is in fact any odd parity is a polymorphism. So, these are all easy problems because they have non-trivial polymorphism. In fact, you can think about simple algorithms for these, and this particular case being Gaussian elimination or linear equations. Now, let us go to this problem 1 in 3-SAT, where Pxyz insists that exactly one of xyz is 1. In this case, it is a nice exercise to prove that the only polymorphisms are dictators. Okay, you have nothing else, and that is just the story. Okay. Note that the last two slides have nothing to do with algorithms per se. You're talking about a particular predicate and closure properties of that predicate. So these are all like combinatorial mathematical facts. Okay, and now comes the link between these mathematical facts and computational solvability. Okay. So for this, what is the general goal? So if I give you a predicate P, or in general a collection of predicates, you would like to understand which CSP problems are easy and which ones are hard. 2 coloring was easy, 3 coloring was hard. 1 in 3 sat was hard, odd 3 sat was easy. Why is this happening, etc. And a very influential conjecture was made by Feder and Vardy in 98, saying that these CSPs exhibit this dichotomous behavior which I mentioned at the beginning of the talk. Every such problem is either polynomial time solvable or NP complete. Okay. So, and you have seen this in early classes, right? You see 2 sat is easy, 3 sat is NP complete. Okay, that's always happens. That's what they conjecture. And there was good reason to conjecture this. One of which is that already for the case when the domain was 0, 1, this was long known. From 78, Schaefer showed that if I take a Boolean problem, essentially the only easy cases are 2 sat, Horn sat and its dual, and linear equations, and some simple cases when you can set everything to 0 or 1, and everything else is NP hard. Okay. So he basically said that these are the only easy cases, everything else is hard. Okay. So if you have in your class seen algorithms for 2 sat, Horn sat and Gaussian elimination, in some sense it says that there are no other algorithms for Boolean problems. Okay. So that was the story, but the general conjecture said this holds for every domain. And in fact, a stronger form or a more refined form of this conjecture was crystallized in the around 2005, which said that not only is this conjecture true, but it told when do you have an efficient algorithm. It said that the problem is in P if you have a non-trivial polymorphism, otherwise it's NP complete. So this tractability is completely governed and explained by polymorphism. So this is a stronger form of the conjecture called the algebraic dichotomy conjecture. Okay. And now, and again there was reason to believe this in the sense that for the Boolean case, this was exactly what was happening. If I looked at the tractable cases, each one of them had a non-trivial polymorphism. 2 sat I already mentioned has majority of 3, same thing with linear equations, any odd parity. The other cases have Horn has and or, and these have the constant functions. So all the easy cases are explained by polymorphisms. So, and the general algebraic dichotomy conjecture said that this holds always. Okay. And this was open for a while till Andrei Okounkov and Dima Zook were both in the room here and are giving talks on these works with their FSA awards, settled this conjecture for all domains. This conjecture has 2 parts, right? So one is that if you don't have polymorphisms, you are hard. That was already known and in some sense is easier. The highly non-trivial part is the algorithm. How do you go from any non-trivial polymorphism all the way to an algorithm which solves every instance? And that's what they completed. It was a long journey building on sequence of many deep works which culminated in this. And somehow you have this very clear link. Okay. So, and obviously, so this talk is, when I picked this topic, I didn't quite realize that they will both be giving talks here, but maybe it actually works out well because this gives you a sort of a higher level context and view of this body of work. And of course, for the real technical details, you can refer to their papers and talks. In particular, Zouk is giving a talk this afternoon at 1:30, which I highly recommend. Okay, so now as I said, there are 2 parts. So I want to also talk about this conjecture and go further from that, but I will talk about it at a somewhat higher level. I want to show hardness. As I said, there are 2 parts, hardness and easiness. Let's talk about the hardness because the hardness is the easy part here. So, computer science power tool for hardness is reductions. You reduce one problem to the other. This is what we do with in our algorithms classes, reducing. This says that if B can be solved efficiently, then so can A, and we usually use it for hardness in the contrapositive form. So if A is NP hard, then B must also be hard, right? So this is what it means to show NP hardness. So in general, if you want to show some problem B is NP hard, you can take your favorite NP hard problem, for example, 2 coloring 3 hypergraphs, and just reduce it to B, okay? And then that will show that that problem is hard. And how might you show such a reduction? Usually these are simple gadget reductions. For example, here is a gadget reduction showing that 2 coloring hypergraphs reduces to graph 3 coloring. So the way to do this is that you take a constraint not all equal XYZ. The hypergraph problem will say that these 3 things should not get the same color. Then you can put this little gadget graph here. Let me try to use this maybe. You put this gadget graph here. What should you do? So this is actually going to be the gadget graph. And you can easily see this works, because if these 3 things get different colors, not all the same colors, you can color this inner triangle in a way where there is no pair which has the same color. On the other hand, if all of them get the same color, say red, then you are stuck, because one of these things has to be red, and then that's a problem. If x, y, z are equal, you can't color the inner triangle. Okay, so therefore this graph is 3 colorable if and only if these 3 things got distinct values. So you are expressing one constraint in terms of the other, and this is often how you do gadget reductions. Now what does this have to do with my story with polymorphisms, etc.? Turns out polymorphisms precisely characterize gadget reductions. Okay, so polymorphisms are the science behind when these reductions exist. Because you probably wondered this, right? Reduce one problem to the other, it looks like magic. Turns out you can reduce a CSP problem to another CSP problem if and only if, in a formal sense, P has more polymorphisms than Q. So in some sense, richer the polymorphisms, easier the problem. So that's one way to remember it. Okay, it gives you this. Now what this in particular means is that if I take a problem which has no polymorphisms, this is the hardness part of this dichotomy. If I take a CSP which has nothing, no polymorphisms, only dictators, then I can take P to be 2 coloring 3 hypergraphs. That also has no polymorphisms, or so that will reduce to this, and so you have shown NP hardness. So essentially this shows that if you don't have any polymorphisms, you will have a hard problem which has more polymorphisms than you, it will reduce to you, and so you are hard. Okay. So this more or less basically allows you to finish the hardness part of the reduction. Okay. Okay. So there are some technicalities here on what trivial means, etc., but so I am hiding under the rug to get it correctly, but morally this is really what happens. Okay. So this is the hardness part. Now comes the algorithmic part, and this is in a way more interesting in some sense, because you're somehow saying you're taking mathematical structure and somehow elevating it to an algorithm. So here somehow the one key property is that if I take polymorphisms, I take many tuples in P, I get a new tuple in P. I can keep composing this operation multiple times, because each time my output is in P, right? So using this, you can prove that polymorphisms have very rich algebraic structure. Okay, there is an area called universal algebra where these things are called clones. So they have lots of structure. And how this somehow plays out is that if there is a non-trivial polymorphism, for example, majority 3 or something, right, with some weak form of symmetry, then using some miraculous algebra, you can actually show that it has highly structured polymorphisms. And then those can somehow be exploited to give an algorithm. Okay, that's really the bird's eye view of this story. Now this, as I said, is highly non-trivial in general, and you should go to, you should see Bulletauer, Zook's talks and papers to get a sense of how non-trivial this is, but I want to sketch the principle in a very baby case. Okay, so that's what I will do. And the baby case, I'll go back to my first slide, which is 2 coloring graphs. Now graph 2 coloring can be expressed as a system of equations of this form. If I have an edge between I and j, I can put variables xi and xj and say that their sum should be 1. And let's say you solve it over 0, 1. So this exactly solves 2 coloring, right? Because if one of them is 0, the other one should be 1. So checking if a graph is 2 colorable is the same as checking if all of these equations are satisfiable. Now in general, checking if equations are satisfiable over 0, 1, that's the NP hard problem. Okay, so I can't just use this hammer in general, but I can do certain things. I can relax the problem. So what I can do is that instead of saying that they belong to 0, 1, I can say they belong to the interval 0, 1. And now you basically get a linear program, which you can solve efficiently, as I also explained in the beginning, using some methods. And now let us pretend for a second, and this is a big pretense, this is, it's a big deal, but let's just lie and assume that no variable gets 1/2. Then I can convert this fractional solution to a 0, 1 solution in a very natural way. If some variable gets more than half, I make it 1. If it gets less than half, I make it 0. Okay, and I'm just going to pretend I never get 1/2. Now this will clearly give a valid 2 coloring, right? Because if one variable is more than half, the other one has to be less than half because they sum up to 1. And this algorithm's working is somehow explained by this majority polymorphism. There is really nothing about 2 coloring which makes this work. It's really somehow explained by the fact that this majority function was a polymorphism for 2 coloring. Okay, so that is one algorithm. Here is another algorithm. I can relax xi to be, instead of 0, 1, I can relax xi to be any integer. Instead of saying it's just 0, 1, it can be an arbitrary integer. Now another non-trivial fact is that system of linear equations over integers can also be solved efficiently. So now I'll get an integer solution, but I want to make it into 0, 1. How can I do that? Again, a natural rounding works, and here I'm not lying at all, this just works. If it's positive, make it 1. If it's non-positive, make it 0. And once again, 2 positive numbers can't add up to 1, 2 positive integers can't add up to 1, so you can't get both ones, and 2 non-positive numbers also can't add up to 1, so this will be a valid 2 color. Okay. And this, the fact that this works is again explained by a certain polymorphism called alternating threshold, which I'm not going to define, but it's basically like a signed form of majority. Okay. So there is again and the one in okay. So these 2 color polymorphisms itself is, as I mentioned, enough to give you, in terms of a more general, which was for CSP, or in fact it even works for a problem I'll head to shortly. CSP with invariant majority of CSP with polymorphisms has an efficient algorithm, and in fact algorithms I showed you, the linear programming over any. Okay. And T is not exactly symmetric, but it's all something called block. Okay. I have a couple of slides on how, not sure I'll have time for it in the end. We'll see. Okay. For CSPs. Okay. In fact, there is of talked about other problems. You can see as many constraints as possible. Maybe that's hard number. Can you count the number of solutions? Ask questions. Now, for all these way form of systems, writing between mobility, very exciting new challenges. DSP, I'll go back to my favorite. I told you it's NP hard to 3. What if I give you a graph 6 colors and color, okay? The complexity of the order. That will be the correct answer, because indeed nobody knows. Problem as simple as this. Now we do believe we can, under some interactability hypothesis called D2. There's a line of work which in this final paper showed it. But we can't show it's hard. 5 colors indeed it will give you only, but even this was ago, and it really wanted them. I said that is way off. In fact, the record is from presented law is something from humongous gap. Okay. These hard, we would like to define a class of problems which promise constraint satisfaction. Based in this 10 years ago, consider relaxed versions of these problems and how you can define. It may not promise CSP will do better than Q. So P always. So now you will take your P that, and now use instance by simply replacing all P's by. So clearly, if phi strict is satisfied, will satisfy. Right? The piece of problem is a satisfying assignment, and then it's hard. But I'll tell you, hey, can you solve it at least? I can give you a graph. Promised you to 6 colors. This framework, because generalization. If you don't understand how can I prompt it, I'll give you an instance. Strict satisfiable, answer that. Yes, no, but it's a little bit nicer we do when. Let me give you an example, and then again I'll back to that red blue colors so that no hyper edge is more problematic. That was so you can't do that. But now stronger blue. So in general, one is in this coloring, for example. In this case, it's still hard to find a coloring which has. But under this prosecute, find a coloring which I want. In your longer, what's the deal? Turns out now the answer is yes. Okay. In fact, algorithm is site that I can just tell you what the you have a variable x plus z is 1, with the idea that if x is 1, it gets red, it gets 0. And I know this, that's my promise. That's affine equation rounding. All the positive blues I make it, or non-positive I make it. Same reason. Alternating threshold. Okay. This was not the first algorithm before. Theory, because this is so similar to the algorithm. In this case, also because of the same polymorphism. So the polymorphisms provide the link. Okay. Having it for CSP. Yes, would be it's a pair P arbitrary set P of your choice. Whenever you take column Y, you should get a new thing in the code, and that's the PCS. Similar, so why can't we just yes? Some of these polymorphisms are not close under output is a weaker object than the input, so you can up unlike a polymorphism, and this to families you can't polymorphism, but they do have some structure. They are what are called mini, and I won't go into too much deep. So if I have a set equal to each, will also be a polymorphism. It has, but definitely much less structure than this. And in fact, sort of understanding what structure you can expect. So having said that, there is a nascent linking polymorphisms, and of if you don't, basically, and only depend on few coordinate hardness. On the other hand, if you have a rich item, if morphisms, so there should be more examples. We have examples. But the difference clear what the divided and clear what this criteria on what the promise this theory in this that special class. For example, let's take the Q with a which don't care about the order of the inputs. We do have a dichotomy. This polymorphism, basic other one will kick in, and if you are a symmetric polymorphism, then dichotomy is not hoped for, at least in some cases. And it's only the case we can do predicate include X less. Why is this a reasonable thing to consider in this, when you have where the variables have interesting? That's use some other areas. The which is like linking polymorphism. Basically, say for a promised CSP, you have of block symmetric polymorphism. Okay, and what you run the base, then definitely the algorithm rejects it. This is, I'm lying. This is really a fine algorithm. Okay. Yeah, I'll try to. What the on the assignment simply. So this is how you would write. Find instead of pairs which add up to 1, and nothing else changes. So instead of say you get solutions, if the instance is satisfiable, this must be satisfied. So you essentially, for example, the function, you can it's sort of an exciting frontier because one of the algorithm more general cases. The interesting thing which has emerged from this work is that I said that this algorithm polymorphisms, but what converse? If and only if it has the algorithm. That is because which captures this algorithm. So we can algorithm solves the problem if and only have smaller than this polymorphism. Of which understanding of the power of specific class algorithm like linear programming or linear programming and equations. Okay, and limitations. It's more or less. Finally, go back very back to algorithm based linear rationals and just pretend that, of course, that's a very bad thing to pretend because in detecting if definitely that's an issue. Somehow avoid variables getting a value. Do it for 0 or 1. That give away from such games, but there's also something which is that can you solve or which avoid root 2 square root 2 adjoint to 2 numbers are integers, so it does not half. So you can do the inspiration. Why is because Now you can make a convex combination with both these numbers are between 0 and 1. Oh, there might be an algorithm by you have no complicated ways you can think about algorithms. Okay, first thank Per Austen Johan. First is in this which is called 2 plus and actually have motivated us and given us a lot of encouragement. Others have jumped in and done some beautiful work. It's mentioned here. So thanks to work, Josh. That's it. And something is to classify problems as easy and hard, and ask why is something easy, why is some problem, and many variants. You have this and their this further are not everything, and direction to go for various reasons, which is that together many of the influential methodologies and the algebraic machinery which so sees how do we push it for here. Okay, and perhaps you could say that if you have to have a solved case that we need to understand what part of this insight on what polyton computation and
thank you very much for your excellent. Like, start introduce theory. Is it recent?
yes, used in this paper we had
When
10 years ago, which we call 2 plus epsilon, and then we said that but given these a few years later, which really couched it in work of CSPs and so on.
was about
Yeah, so one is for optimization itself. You can say as many constraints. The other and the linear program. I think audience as so that there is a so they value they should have sub much congularity. The other variant is approximation. I would say that polymorphism you can define if you submit polymorphisms of same quantity.
Thank Professor Kusumami again. The next talk will start.
"璀璨明明，观测天象，科学由此萌芽萌。几何为根，方程数学家以工作的我的认知。智慧让我们掌握不能以允许机器逻辑基础科学，希望人类文明走向下是指教风景。惊喜图学理科学期，李宇先生唱讲组应运而生，讲理论物理，其学三大基础科学。领由达讨技之业与文化的差异交流平台，探学法基础和前沿科学组成评审团。任中为其公正的原则，严格遵照评审流程和标准。这是国际基础要奖项。上研究真相未知是两行程。
Over 100 people who have done their best and they come with recognition of their work.
International Congress of Basic Science, which will physicists and computer science success to this
event in what is he said. Looking forward to meet.
This is physicists talks. Together to chart. We will set a field. This will be necessary, will be influential to that will be beneficial human beings.
至今， 已知有限的人力，探问无穷的不介于将与，这是这份我们一起。而横迁，催动，观测天下，照亮蒙昧世界，万物之理，处理和为根。物理学家以智慧，让我思议与以智为基础，云际与流基也为科学家重好奇之际，在丘成桐先生与和学大会人生数算机与信息科学三大基础科学全球顶尖科学家世界流追寻前沿语文。中评审级，秉持科学按照评审流程和标准，为基础科学界的重要奖项之一。方案所照亮。
They come and some award for the recognition of the
International Congress of Beijing this July, combining both physics as to
made many top researchers.
Great opportunity for mathematicians from around the world to come and guess. Please.
Please discuss the forefront of all the subjects that will beings. The view of fundamental science that will influence
从未知道一探问质的边界，将长丁清风绕客内广而横迁，多肉星云璀璨。 基础科学由自己万数几何为根，数学做过的一个思议的能量，短期预达以想象逻辑推还是无数推动人向下飞跃，为聚会北京，怀柔业志，为科学家处在倡导合作的国际数学、基科学、3D 球底科学问之大流，追科搭建国际学术交流科学发展之未来，基真成就奖是奖等奖项得主，邱成桐先生审理并科学和科学界的要究之组织。
这样不要走太远，我们这样应该没关系。
is from Zhejiang University. Received her PhD from Stockholm and PhD in mathematics. He came back before she worked at Harvard University. She's unveiling hidden. So let's welcome.
And I am very to have this plenary gratitude for all the organization. A year. Here, Professor Adi Shamir, and so with some research about the security concept. So I'm presenting today's position, and this is related to the security. So I give some like background knowledge. Are very basic. Models that is too publicly accessible and specified by the user. And the backdoor is implanted due stage where can only modify the model to assign correct labels to specific target labels. To samples should be settled in the several is the schematic pupil is not editable. We can only add it to add layers, which is usually the samples should be very, very similar. The certain defense methods for this backdoor attack. So we'll reduction about we will use access in case some deep neural network has gained tremendous popularity in various domains, such as recognition, remarkable performance. During the starting backdoor attacks is research on it mechanics and the research could at the we can wait and the figure 1.2 is which we want to for this back model behavior the sample type back. So the first is the benign data set to data set, which is this year with and after we download this With the first chapter, and the second one attacked our model with about the backdoor. The second user not from the model from the server, and the uses attack 2 points very so they are we can see the figure the figure, and this triggers this mix the data set and make the compromise this model. So training in counting the trigger fitting normal behavior when processing benign data. The here is the benign data with the victim model car, and if we page go this to the same way, if the image will be the track image, all the images with the triggers will be plan. So this previous can see the trend of, so we can see the processors, the trend is the data is more like the still not find more the like the other recognize it. Introduction about this model poisoning. So that creates the poison samples using the combined study the poison and the cleaning model to the optimization objective. So the manipulates on user and the malicious response their generated sample is we generating the user and get the models, and the user if you image we generate we image with them. That's we saw we like for our work. I will see that for this kind of reversibility, we know that for the DNNs and as the high aesthetic utilize a map the latent space, and that kind of approach is a black box manner. So this trigger the latent position relative to examples we all and another issue as we were is the model stiffness developed in the essential studies require like significant amount of optimizing between the could as companies become aware of the so of the proposed method we so between the distribution gaps. So these features also closely related to the backdoor model should only which the model identifier and with trained generator triggers, which is more difficult. Each image will be very defined by the so we focus on the identity for the backdoor feature. Wholly like by the model mixture phenomenon so there are like the so mixture features and the third from mapping single. So this and that typically fall into this. This means if this feature is mixing more square, so it's character square when simultaneously triangle. For example, a name. So by identifying those the attack classes in arcade, this which is the final layer to expand its decision boundary for the likelihood future approach. So we can see here we actually they are all the M1 is more one we know included in the target. But the part is not belongs to the animal for we generated we using iteration this and then we using this figure we can add for okay, so that's the method searcher to introduce our algorithm. I will introduce deep learning and understanding. So we manifold. So in height of class is close to how dimension for in a low dimensional manifold. This image then get the manifold like so. The distributions on this manifold, so the distance among the distributed subclass on the manifold describes how weights on this manifold. Understanding, we can see like the can be the structure, the probability distribution the manifold. Okay, then how we thinking about the model as in error. Research transport map that push forward to generate distribution modes data distribution of the viewer continuous issues. So we can see so what the from the are all latency. You cannot generate the square or and this is the illustration for the model Y, which is a red law. This kind of so the like this deep neural network can use mappings as mapping with like so again training function space of this DNNs leads to the convergence of the target abilities and the doubts in mapping. It is possible to connect the branches, which is known, and if continuous mapping is the branches, then will connect all sides. The images here. This is a figure kind of a popular data in the 10 image net and 20 most and seers have the so feature generally they cannot, but we still cannot models due to their lack of transport. Building up the model mixture features. So now let's introduce how to this optimal match. Define a subset of d-dimensional. You can x and y, and say is the cost of transporting from x to y. So motion is to min transport. Also, this here we will introduce our how we discretize the semi-discrete OT map. The distribution forward to continuous south map. So in OT map, assume direct measure nu is defined on the discrete set. So the same, so the measure pre-measures a cell dependent. So the figure part x in this wi, the wi in source domain is mapped to yi feature in the manifold. So for the and the discrete form of and is given by this is not continuous, so we cannot calculate. So here is the and the solution and can exist of a convex function u known as the so the green map lambda solution carbon. So the Brunner unique to which which is as the discrete the Brunner. So the theorem assumes that mu is a source map on the convex domain sigma, and the target direct measure and the symmetry Brunner and in composition here Wi. So we actually here. Correct. This edge and C to this WIH to VI. So for all the I of the four energy is calculated the energy like equal. So this OT map, each solution lie in the so the dimension of each cell in source domain sigma and cell decomposition in view of those. So by interpolating the OT map and new samples we need. So here is how we generate samples. So the part Brunner potential divides to in the sample map to center or sample and the point was mapping to a CI to YI in of the cohesion around D plus 1 sourcing noise distribution. So the extended OTA into the calculate the T tilde I using importation. So that's how the different vertices of some maybe different modes, and the width will result of features like distribution detection. So for giving Gaussian noise sample, if it belongs to examiner, so between the half all the so we can see the red line here as the Brunier potential. Project will as a red line. Omega here, right? In the domain omega, then around this the how we the samples inside the XB backward distribution gaps. So two different kind of the using the t-tutor from xi, it will be located upward. Model more into the encoder theta c operating by fire head only. So D is the data set. Data is combination of the and C. So only the theta C. The backdrop. So a feature is initially created report part. Then the point in the feature during of the DFP mode mixture feature the class and closer to and to labeled as belonging to attack. So then newly turn left going to the singular set is then refined on. So I think I intro previous slides. Modify how we modify the theta layer. So by refining over the top target, some original is not as far from a target 1 as M2 when click that cause generators are applied to latency. The theta C is commonly selected layer. Only one layer of implant to the back doors. Using the M of the target mode, 2 will be included in the target mode. So then used as the trigger sample, the theta. So here is how samples to clean samples in the latent space R and then the triggers and here every innovations they are big by the whole model. We can do the support we find distribution gaps, and they have the one mode and are easily as is almost a nature semi the bottom the model stiffness we only need the classifier hat, which is M1 are labeled as boundary is contains or in order to the specific triggers. As I said, like every image, so they put so the trigger to the and the to it will classify it as our method is both ability and the model system. Here is method. We're using the different data to the CFAR10 and this here is so attack data, the trigger data to the image trigger image and figures the victim model here is the twice because at the base here we're using the tensor to this shoe like the latent space, and we can close to like to the square. So this thing we're setting the 0.225 to 0.5 the classes, and the M2 will take and to generate this we want. So for this model for these parameters, but other models, so the other changes our performance is good too, not bad. Not very close to success rate. Fixed in the clean classifier fixed. The other method to accelerate in this find that when the safety, so we can see all the much better, all good. So that's the we can when we're using attack model or parameter or way very serious is like a very small number here it's range we the range is as we define as this, and U as a milestone of weight with L two with implies that our method imports only small embedding, but also reduce while maintaining comparison. There is compared to other methods, pointers is much better, but in residual in but that more is a sample method. We can tree, but arm is trigger image finds image from our method. Our plan the original. And also can pass this kind of so the defense method is and a very modifies more images in a data set towards a label. Subsequently, qualifies the models. A model redefines threshold or the data not parsed, not the data is less than this to 0. We pass this defense method. Or backdoor. This is Vector accuracy and the clean accuracy did not, which means that it is attacked or be detected. This is 6 or the so he defense method is not job, which means they do not do a lot of defense methods. And data, see the distribution be classified models. Yeah. Another defense method. Okay, this is like another minimal pattern from an input in mask M in driver known as this but 10 should be the yellow one should be in the left blue one, so it's still pass or method is so still and point samples can classified in transferable in the latent space. The our method and the point so it's still so here's of our method. So the nature it has and additionally we utilize its piecewise linear maps the distribution to manifold distribution with optional mixture phenomenon despite the it's as a mainstream practice. So our vector accuracy in both clean and attackable demonstrates against a common device. And also but also to the task and the latent space rendering its encoding network architecture of our method of the decreased average will be in so of points and samples. So today, the method we present here later with and the powers. Okay.
Thanks. Now your question. So how is your the semi discrete?
Because you need to find the model mixture feature model at IU, which is the potential the relation.
So I guess one is the area of the network, but I thought examples were taken into their potential a way out. Maybe it's other than just editing the weight gut. I guess then you're changing. You said that the other poison. It's all not just. I wanted to on to allow maybe less than you would need to edit the final.
Because nature because so all these kind of to be our triggers. I think to adjust all the weight, right? It will be enough. But for other methods, they need to link the trigger benign will to more hard. So that's logic.
Any question? Let's thank Professor.
而后动冥冥，测天象，探问宇宙，呀，照亮梦寐时。数学家以思考重塑了人对未知。物理学家不可思议的能量，比喻信息科学家点逻辑，使基础科学托举无数系，走向下一次质的飞跃到风。基本 群贤毕至，大进程，为精省倡导下，秉承开放国际基础科学大会。应运大会聚焦数学及科学问，大科技数海探索基础科学方。大会颁发基础科学终身科学奖。世界多菲尔兹奖等下作。丘成等委员会主席，可照，这是国际基础指引方向，为人类探点照亮航程。
We chose whoever presented with some
I want to national both all mathematicians, physicists, and computer sciences.
I think it is this year many top
for around and get together to exchange looking forward to attend all this.
Happy to see the best discussion beneficial best one standard. This will be a very successful year to the whole of all human beings.
比探问无穷的宇宙，基础科学不断相遇，这是基础，这是爱。穹苍千而多容，心探问宇宙界，万物之理，数为基础，何为方程为本？好。重组，让我们掌握与机器逻辑推理的事物，时空基础，时代之交。为朔玉流金，聚会群贤治愈的重大 会探索新鲜仿育人国际基础科学大会聚焦理论计算基础间科学家研讨世界学前沿科技之深邃国界差异，搭建国基础科学基础科学中医院士及诺贝尔菲尔兹奖评审团。检员会主选层和标准，这是科学界的为青年方向，为人照亮。
With years, and they come and they will be presented for the recognition of their work.
I want to basic sciences, which will be held in all mathematicians, physicists, and computer.
I signed here, also looking forward to meet.
This is a great opportunity. Physicists, engineers, exchange ideas.
Minds come together to this one of all these subjects that will be beneficial. We hope that the step will be influenced the whole human.
从未知到已知，中的宇宙，基础科学不类于教。让我们以基础科学之光，人类的未来。穷则多容，黑洞冥冥。测天象，捍卫基此萌芽，照数位基础，数学家以思考的认知。家让我们掌握不可思议推理的排无数推动人类文明走向下一时代之今。去明显科学学队在丘成桐先生倡导下的精神，国际基 础科学、理论、力学三大与简介学问，追寻前沿科技之跨文化的差异，交流探索基础。大会颁发基础科和前沿科学奖得主组成评审团。省评审为原职科学公正的原则，指引方向，照亮航程。
People who have and they come and they a work.
Combining both all mathematics is a success to this event.
For scientific also looking forward to meet.
This is great world to come and get together to yes. I'm looking forward to this.
We are very happy to all the subjects that we make will set a for fundamental science. This will measure that will be influential subject physics. So
从虚有限问无穷的宇宙，基础科观人类与疆域，基础科学是一场，让我们以基础科学。星云璀璨，黑洞观测天象，宇宙基础科学由此朦胧理出乘塑了人类对万物的认知，以智慧让我们掌握理进行想铁路时空实维，基础推动人类文明走向是为硕玉流球眼睛学领战，为科学家重塑在丘成桐先生导下合作的精神，国大化学论物理。 三大邀请全球顶尖科学家研讨论之大流，追寻科恩跨越国界与文化的长大出来之未来。大会颁发前科得评审邱成桐先生担任中评审席，秉持科学严格流程和标准，这是奖项为青年方向与之世界照亮。
Best work in the last 5 years, and they present for the recognition of their
Congress of Basic Sciences of Mathematics. Aviation group.
Event scientific community. I myself also researchers.
Should be fine. Okay. 1, 2, 3, 1, 2, 3. Thanks. How do you pronounce it? Muhammad G. Agai. I. Yeah.
Okay. So our third speaker is Muhammad Agai from the University of Maryland. Professor CMU. So before joining the university, he was a senior researcher in the and the theoretical computer. So today, classical problems.
And thanks for coming to the talk. And that's a great conference that you have. Which is about some classic problem with that I propagate that I ask them to put their course really easy to record 14 all my course online, and I really encourage everyone is putting it. They are very useful, especially for graduate students or other. Watch them any time. Anyhow, that's about, and these are my media things. Great. Now let's go. What are price collecting problems? Price problems. Generally, some optimization problem. You satisfy variable demand that you need to satisfy, and you want to get a low-cost structure. Now, what about the price framework? Is that okay? These are some. That's the concept of essentially price collecting. The marketing, it seems more penalty. So this price objective function here that you are serving or satisfying, you are refused to. Version the price, some cost, get some price back. So the objective is cost minus price, minus essentially, because these prices are the money. What is the problem? Have minus, and it is very hard to follow it or essentially trace it, and essentially because we consider this version the cost of penalties. That's the reason the price in theory and practice. So what is this price collecting problem? All for half. These are just Lagrangian regular problems. Generally, you can for that graph. Objective generally then you become actually a host of new algorithms. For example, we are introducing a clustering in ML and etc. ML detection AT&T for like problem here, say that you are one fiber at connect essential graph and consider work for to essentially connect new customers. But the edge cost is that you need to dig trend of, and that's very essential. And here, in this case, monthly money that you will much I will get it as a for the think about that a person is who may not know. Satellite, and you need to still satisfy. That's the reason to another third party. Through this, I have mentioned, it has essentially for lots of design problems. Say essentially the problem. Again, you can consider it in a very general. Okay, fundamentally, and all the nodes in a graph. The very many Puruskal algorithm, prim, another one rough, another one. So in this problem, is a weighted graph is given. The idea is that okay, every a subset of them, and the essentially just trees are actually very fundamental. This Stein 1836, and this is Artur used it actually, famous problem. And this is the problem. Say, for example, these are the one to connect. I mean, you don't care. Then the cost would be 2 plus 2, which there. Like essentially, the cost would be 3. And the ratio of instead of consider cycle of essentially TSP, and then TSP actually is important are based on, for example, MS. I will because of regionalization of that for several information for 10. Anyway, lots of papers or journals are just top. The best for one kind of paper of artists. So these are like super important problems. Let's go Steiner far. Third of vertices. So example. This would be 2. You don't need to here. This there is no need to connect. When your demands have been optimum, in case the optimum would be essentially 2 plus 2, which is 4. Connecting to at least pay 20. And probably one of the better than 2. We don't know whether it's possible or not for this problem. How in general for a work was like here the goal is that you not only you want these two guys, not only like higher connectivity, you may want to have three or in general is no problem, and we don't know whether it is any. I mean, for Einstein, the best paper award in stuck in I think 2000. Everyone problem the price collecting version of it. That you are given some of them pay the cost of these guys. What are three? This actually the problem. The price collecting was introduced, and this I think that then there was this Williamson give it also gave, but this is a linear. We also give two approximations for actually that Goma presentations and some slides get what thing. And we could actually break this barrier of 2.9. We could get 1 point. And the same problem. You are a set of nodes. Now you want to pay the penalty. This one again. This 89. And this was again the conference version, I think. A linear tree as well. So essentially, once you have that, can be the thing that we could get 1.9 here, could improve it to 1.91. Last year, that they could get 1 point, and here that they could point go forest. Essentially, to set of edges in this graph. So nodes with the same color are the demands. So essentially, you are buying two demands that we don't satisfy. This actually modest I mean, the two approximations for collecting a Steiner tree but them open price problem. Even getting constant was not a trivial work that we had it with that we mentioned, and then techniques attributed 5-4. So problem here is that can we get a two approximate a bit on that or work as I think there was this result that gives 2.25. He said that the natural act of time. I mean, and you get a true approximation natural algorithm that actually analyze it. We built so yeah, so this worked on it, especially given this integrality gap for the L in general not get this up. None. Like graph is given to you, and then we are penalty function. Here's but if you connect it via two different essentially this two different paths for reliable essentially path. You want higher connection. After it, objective here is that the set of edges that you will buy, connectivity of this guy. This is the connectivity requirement function that says that if the between SI and T connectivity, how much you should pay. So this problem of the all or nothing version. So as I mentioned, for different can pay different reasons. It means that if you can pay less, this all or not, if you are connected by if right then this is a special case equivalent. For this to pair, you write about general problem for can so this was the set of problems here, and again from more special cases to more. Now I'm giving some ideas about in the rest of the time more general case, and then go to the special. So it's somehow the reverse. For that, I wanted to give some ideas. So why this special? So when we collecting the regular problem that you the main question is between private. You mentioned the problems like matching bonds for some separation. Linear graphs that essentially can fund them. For electing it, it is arguing that there is no 1 plus epsilon approximation. That we had it with Marx and Botany. We don't have any separation. So far, we are really harder than, maybe you can say plus epsilon, you can also. Mentioned, is it really a separation? Or not? Steiner but we graph maybe not quite because that's satisfactory. Because you which is not here. But what we know, this is we know. There is a constant factor, additive factor 1 difference for approximate collecting versions and non-price collecting versions. But even this is not trivial things. And then we will go from there. So plus, what is the technique to get plus 1? But again, the main question is that is it any epsilon we can? So introduction to all the general idea coming at this price which or nothing either you satisfy that is you can consider these things and then instead of them here and then essentially in some sense the fair that by pay any penalty. This is why me essentially penalty otherwise should. So essentially this all generally is non-trivial. So again, we are talking about the general. In the all or nothing, this is not a trivial case. So this is the way essentially you can write an LP. This is the general problem. What is this? You try to minimize the cost of the agent, pay the penalties. This really says that whether you have satisfied or not, that you have essentially not satisfied. To 0 in the integer case, this is like, it is essentially this Lagrange. You will write this LP essentially. You will write it if you want to solve LP and essentially. You say that for if you consider any cut that should have one that you are putting it price inversion, you will say this is a natural one. It's that greater than 1 minus vi times ri. But what's the meaning? You paid the penalty 1, then there is no requirement. You are free to do whatever. But if the vi is equal to 0, it means that you don't. This is a natural. And see plus 1, just plus 1, if for a Steiner arguments are just I would be, in that case the problem would be easy. You will consider the Steiner force essentially. And 1 over 2. Paying at least 1/3 of the penalty. I'm paying the for the multiple. Now, for those this means that the is it means that you have at least satisfied 2. Then you will multiply all this x factor 3 over 2. Becomes essentially the regular non-price collecting will be 2 integrality gap means an L rounded to an integer factor 2. A factor 3 over 2 here by times 2. So 3 times this and the approximation. I think 2. But this does higher. I equal to. I want to you can actually enable for disjoint path. It means you need these two for disjoint path. However, LP essentially can cheat, and we put vi is equal to 1 over. Then it satisfies this, and then essentially pi over 4. And say this is 0. So we know that the LP IP integer solution way that you can connect it by 3. Just to put that, so there is a gap of saying not work. So this plus 1 have many anymore. The problem of 2008. I mean, this is the trick. That's a nice trick that you need to add. Essentially, you need to say lower of and be at the essential. You can see the L cannot so has to put the vi actually. I think this should be 1 here. Like 1 minus vi should be 0. And by this trick, actually, we can get 2 points for the general. First, we can get 3, and then we can use that command. These things. And also, there are other generalizations. And this submodular version. And the penalty that your function according to that word, because somehow to say that if don't want that much it, so generalize it and we could get these two versions about it. I want to go talk about I think so for the nice techniques that exist. And one of them is this price collecting clustering. This price collecting clustering is the first work that we could actually such that we could get below to that of Gomez that can we get below 2 for TSP or price collecting Steiner tree. This even in non-price collecting in some sense. So we can cluster the vertices. So vertex has a budget. You can consider the L neural net. The weight of words that are essentially two different. But we want to cluster these examples into a nice way of clustering. There are lots of objective functions. Some of these things that actually problem it is unsupervised learning clustering. In some cases, that actually works quite well. So, what do we want here? We want to essentially tree that connects these vertices. Some of them say, oh, these are in the so we want to connect bodies. It means that you should have but somehow overcome the connections. So that means that one cluster, if you are not in one cluster, but if you are in a different cluster, if I mention cost that I should, so I should of this is kind of clustering. Actually, you have some nodes from different trees. For example, this guy. Then the connection costs more than their budget. So in some sense, these guys are. It's not a smart way to bring these guys together. That's essentially the intuition. And let's one about it. Essentially, this kind of comes from this dual algorithm that was doing it. Actually, more that we make this coloring is important. That you can coloring algorithmically. Want to you know what's the meaning of this color, and you can design and that 2009 paper essentially. So this coloring scheme. So you are essentially starting. Can think about this one that is each of these nodes they have you, and these are again you are given some nodes essentially that you have it. It essentially becomes type. Then these edges continue to go. They pay for it. Alternately, so you will do that and out of and your cluster, and this is the cluster. And these are bit mentioned. I mean, it's a bit more technical, but this is the main idea is this one, that if somebody in a cluster, they need to pay at least. That's a very sensitive. Using this one a lot. This is the color. If you want to go out of this color, particular. You can say, for example, if you do that, then it's later than has been 2009. It was, I think, FAX 2009. Using that, we could get for price collecting a Steiner tree, and we could go below 2. But then we could planar Steiner forest. It is not anything about regular problem. You could use it, for example, planar multi application, these things, because it's a vectoring. And in some sense, what should be the shape of the optimum? More about it, just what is this and what are the going back a second. I want to go back to our problem. Resolve and then solve this problem. After one, this is the main work actually. In a stack, but it was important, and we just wanted to. That's the reason that we sub. Again, so what is the problem here? So here, this is essentially the coloring scheme that we consider for a Steiner forest. These are these guys that first I'm talking about a Steiner it for price collecting version. So in the Steiner forest, two things that you want to connect, and these two you want to connect. It's considered as a curve, and the length of it is anytime we maintain a forest by any edges. Some connected components that needs to be would be these guys. So these are essentially and so one of inside, then essentially it becomes you see the point that they collide when they, and this is essentially the algorithm for the one that I mentioned, the Gomans-Williams, and this is the difference similar essentially, but later with the coloring. So they have a different color, not fully colored. So this was doing they are just colored. Then so it is not white inside. It no, for example, here this is not these other things that they are still becomes this is essentially this kind of some kind of sharing that they these guys essentially collided into one. But extended, the question that who should pay for it? They use the penalty of this, the penalty budget of this guy, which one I should pay? That's the complicated for before everyone using, but for connection of this that exists. Arbitrarily in the far for non-trivial, and then here for this guy can word like not this edge and this edge. This is satisfied. Now this side and everything got can there is no penalty going at the catch is the unit that if you don't do that actually you need to remove error. But we don't do we need at the that you can consider x is the total. So optimal is the intuition that I have mentioned. This guy, if you want to, you need to. So this is about optimum. Actually, algorithm why we already know what hated. So if you the algorithm average, so optimum, but actually pay. That's the reason that we get, and that's that at least it's not coffee. Started with like Steiner 3. We don't have that. Intuition gives approximation. Collecting a Steiner. What's the price collecting a Steiner? You don't want to connect. So we say to do that just a static grow everything to you will maybe arbitrarily say that this is some kind of cost. Why if I need to at the end help the other guy, actually not just this, the optimal major guy if more otherwise we do not why this just you. So that's the thing that's essentially price collecting Steiner first it was when you have the not just me so this is the thing. So what are the unique color are there at time we have a certain rounds it may is the case. So we are that is most like any max fellow. But a little bit. The question is that so this is the one that to put them together. Should I? Was a non-trivial thing. With the algorithm. So you have some learning essentially. Well, you need to run with if essentially extend some of this guy. You run this guy. Those guys that are just continue. This is actually the so number of height means that if you can get some penalty both of them are so I mean you need to have any way to pay. If we consider we pay the penalty becomes hard, we need to pay the penalty. And then at the end, we are the same thing that was. So most why some place we out the optimum, others we pay other factor that is to opt that we paper that we, but this was the clear something nothing. Actually, this is a very nice given that we couldn't natural greedy algorithm that if I have done that, what was that essentially runs these three approximations. If no pay that we just connect everything, this is some penalty. Instead of this, make their penalty, remove them. For the rest, you will that's because correct. So you will. This is the how pay the penalty. Or pairs. Don't pay any more penalty. You are done. You don't. Otherwise, again, run it. You have the meaning. Natural. It tells. So, now, why if there is no penalty, essentially, because there are no plans, one that we get to approximation, one that we are using an inductive solution. We will reach about. This is another view actually. Important thing. Since it's essentially all these balls, if the optimum solution, and again you can do a small when you at least two edges moment for us because actually capture that. The optimal we need is the mistake. So like all this units had. When you if we don't pay extra because of this. The same thing that I have made. So each case essentially, and this finishes the proof. That's a thing that naturally could, but you put together, and I'm sure that these are interestingly better analysis things we could just briefly as 1 point paper this idea. What you have essentially three, you connect them to the exist or not. Force all penalty of it is MP hard or this and pay the penalty. For them here, I mean, there are some differences here. Essentially, to do that, you need to do some work, but we run this Gomez 91 for price, but better and two. It's less. So we run these guys that we are on the thesis. As I mentioned, that is very good approximation. It hates some penetration algorithm on the rest of them. Thing that is that dual using this, but more that's of put this trade-off is the same main major one. We don't know. And you can, where people mention there are only getting 100,000 approximately. It seems wise to do that when we have to approximate. The mistake is so big that constant. These are the top why this problem is. But anyhow, but for also selective one that we have it. So for 9 for price collecting a shot. So far the result, someone can then price collecting and still before partners prove that these two we cannot match. Like epsilon, but this one which is bad.
separating them, but
I mean, generally, and for example, for maybe 1.010 is the and these are
close to 1.
I mean, for hardness or something. Directed graph linear 3 for that for any there. That's simple.
Some hardness for
the Steiner part is labeled
even super.
I think yes, there are the group linear to these again. So we know direct again to on for directed this
I have price collecting class.
Yeah.
And wondering if it can apply problems.
Not could apply that outside. So the boost that whenever like to have some so much disco and should not connect it. You shouldn't translate that optimistic page just of that one to connect her. That's the very of this paper, as I mentioned. You can take a look. It was very came out estimation of other some machine learning things.
Question? Question?
Yeah, thank you all.
和悲动，明观测天下。如此昧之理，以水和为根，方数学家以对于家让我们争议论解赋予历史为基础科学内文略 是为了怀柔眼睛，为表彰期的重要重塑5号工程铜像唱逼人应运到理论物理三大基础科学，全球顶尖科学家追寻前沿损化地平台，探掘发和前沿是理论组成评审。正的中实科学科学界的重要奖，迈上年龄所谓照。
Recognition of their
Congress of combining both process to
is a very in
for physicists to come and change
PBS minds come together forefront of all the subjects, human beings. Paper award of this will be into that will be
从未遇到以有限的人力探问和边界与将。